Okay, so this is under time response chapter. So in the previous discussions in chapter 2, when we did solve for the transfer functions, we modeled them in S domain. Those are frequency response. When we say frequency response, that's in S domain. S is a frequency. Now, we also want to go back again because the initial problems, our problems are all in time domain. So we want also to see what's the response in the time domain. So in order to do that, you take the transfer function which is in S domain. You just need to transform that into a time domain. And to do that, we need to apply the inverse Laplace transform. And to illustrate our first order time response, we can look at our derived transfer function for the different types of first order system. And basically, a time response or output response, time response, you can just call it tau, or you can just write it time response, has two parts. Those two parts are, the first one, we call it the transient response. Transient response. And the other one, so we need to add that to the what we call the steady state response. The transient response, this is the response that hopefully dies. It will be zero when t approaches infinity. So this is a response for a very short period of time. Very short period. That's why it's called transient. Well, the steady state response, this is the response, steady state, when t approaches infinity. When t approaches infinity, then that's the steady state response. So if we draw a time response, so for example, if our input, this one is our input here, then our output, our response, looks like this. So our goal is to make our output the same as our input, because our input usually is the desired value, while the output is the actual value. Here, this part, this is the transient response. All this part towards when t approaches infinity, this is called the steady state response. So that's the two parts of a time response. There are also other response definitions of response. We have the free response. Free response. When we say free response, this is the response of the system when there is no input. If your input is equal to zero, is the input in the system. Whatever the output is, that's the free response. This is usually the initial condition. And we make this one equal to zero. If we assume that all conditions are zero. So for example, in a capacitor, if it's not initially charged, then at t equals zero, there's no output. So the free response is zero. But if there is an output, even though there is no input, then that's called the free response. Another one is the force response. The force response, this is our response with input. Now this is with the input. What's the output if we have an input? So this is free response, no input. Force response, we have an input. And there are different types of force response, and we will discuss them. The total response is usually also sum of these two. If there is initial condition, so that's the free response. You need to include that in our total response. And usually if this is zero, our actual or total response will be just equal to the force response. So what are the response that we are looking for in time domain? So it depends on our inputs. Now to illustrate those response, we need to have an example. We can look at our derived transfer function of an RC circuit. RC circuit. We already derived the transfer function of this. If our output is the current, and our input is a voltage E. And if we go back to our discussions of transfer functions, RC, this one. So we have here our transfer function is just equal to this one, 1 over 1 times S. And just copy this. And you already know how to derive that, so I will not discuss that here. Just go to here, change the color. We can remove this G. And this is the transfer function of an RC circuit. Now, our input is E, our output is I. So if you want to determine the time response, it depends on what type of response are we looking at. First, the first one is we call it the unit impulse response. So what's a unit impulse response? This is when the input, our input, usually R's of t, is equal to this symbol. This is the symbol for a unit impulse. And the equivalent of this, if we take the Laplace of this one in S domain, R's of S is just equal to 1. That's why it's called unit impulse. So if you draw the graph of this, because it's a unit impulse, it's actually look like this one. It's just this one goes to infinity. And when at t equals 0, our input is towards infinity, or if it's a unit impulse, then it's 1, and it's go back to 0 when t is greater than 0. So that's a unit impulse. So if we take the Laplace, that's equal to 1. Or some book uses use of t for this one. That's the same thing. Now, we will apply this to our input here. But remember, our input here is E. So if our E is equal to 1, so what happens? So we can solve now. So for RC, so our E of S is equal to 1. Why? Because this is a unit impulse response. So if that is the case, then this will be equal to 1. So we have IS equals 1 over R times S all over S plus 1 over RC. So this is now the current because we have the input 1. You divide this with 1 and still be the same. Then to solve for the time response, we need to go back to time domain. So to go back to time domain, we need to take the inverse Laplace. So that the inverse Laplace of capital IS is just I of t. But how do we take the inverse Laplace? What's the inverse Laplace of this type of equation? 1 over RC here is constant, 1 over R is also constant, S over S plus 1 over RC. This is in the form S all over S plus A. So if you remember our Laplace table, what function will be equal to this one if I take its Laplace? If I take the Laplace of that function, the answer is S over S plus A. What is this function? That is inverse Laplace. So if we look at our table from chapter 1, you can review it here. or s over s plus omega. And there's no exact value for the s over s plus omega. Here, we have s over s squared plus omega squared. That's cosine. But our problem is just s plus omega, s plus a. So that's not cosine. So if that's the case, how do we solve the problem? To solve the problem, so let's go back here. There's no direct formula for this one. But if you look at the numerator as and the denominator, we have the same degree for the numerator and the denominator. So if they are the same degree, we can actually divide them first before we take the Laplace or inverse Laplace. That's the first rule when we're taking inverse Laplace. Look at the degree of the numerator and denominator. So if it's improper or proper fraction, it depends on the degree. So this is an improper fraction, so we can divide these two. So this will be s divided by s plus 1 over rc. In the answer here, we can just multiply it by 1. So this will be s plus 1 over rc. Then you subtract that. This is plus 0. Then we have a remainder. So minus, this will be 0. 0 minus negative 1 over rc. And in fractions, this is the same as, so just remove this one first, simplify before we take the Laplace. So this will be equal to 1 over r. Then we have 1, that's the quotient. So remember, p of x divided by, or n's of x divided by the denominator, this is equal to the quotient plus the remainder divided by the denominator. This is just a review. So our quotient here is 1. So 1, then we add the remainder. So minus, because we have 1 over rc. 1 over rc will over s plus 1 over rc. And if you look at this one, this is a over s plus a, or omega. If we replace this with, we can just use omega. Omega all over s plus omega. Then we go back again to the table, chapter 1, and that is actually this one, 1 over s minus a. This is minus if this is positive, e raised to at. So we can use that. So the answer here, the Laplace of this one will be e raised to omega, e raised to, this is positive, so it should be negative omega t, or at if it's a. Because we can rewrite this as 1. If this is just, I'll just remove this, make it 1, so that this will be also 1. 1 over s plus omega. So in our case, I can move this one, this is constant, and it will become 1 over s plus 1 over rc. We can now actually take the Laplace, inverse Laplace of this. We can already take that. So i's of t now will be equal to 1 over r. Then we have, or before we do that, we can simplify first. Before taking the Laplace, inverse Laplace, this will be equal to 1 over r minus this one times this one. So 1 over r times 1 over r, 1 over r squared c times 1 over s plus 1 over r c. And we can now take the Laplace of this, inverse Laplace of this one. What's the inverse Laplace of a constant? So remember, when we can actually, if you have a constant, inverse Laplace of a constant, any constant number, this is just the same as the constant. We can remove that constant. and take the inverse Laplace of 1. So what's the inverse Laplace of 1? So inverse Laplace of 1 is, if we look at this here, so the Laplace of an impulse, unit impulse, this is a delta, a symbol. For delta t, the Laplace is Rs is equal to 1. So if we take the inverse Laplace of this, it goes back to this function also. So therefore, this one is just equal to C times that function in time domain. Dirac function, they call it Dirac. So here, it will be equal to this. And next, what's the inverse Laplace of this one? 1 over S plus 1 over RC. It's the same as this one. So it will be equal to E raised to negative something. So I of t now will be equal to 1 over R times this here. We have the Dirac minus 1 over R squared C. And you multiply with the inverse Laplace of this one. It's E raised to negative T over RC. T over RC. And this will be our unit impulse response of an RC circuit. Next, for number 2, we have second type, the unit ramp response. A unit ramp response is, this is when your input is equal to this form. So it's a unit ramp. So it looks like this one. And it's a unit, so therefore the slope of this line is just equal to 1. And what will be the equation of this one if this is our input R's of t and this is t? So the equation of this, if the slope is equal to 1, remember y equals mx plus b, so this is the equation of a line. So our y-intercept will be equal to 0 because it passes through the origin. And our slope is equal to 1, so it's just y equals x. Our y here is R's of t, so therefore the equation of that line, which is our unit ramp, is this R's of t equals t itself. So it's called unit ramp. The coefficient is 1 because the slope is 1. M equals 1. So this is a unit ramp. Now, if this is our input, what will be the Laplace of this? R's of s. We already know that that's just equal to 1 over s. T is just equal to 1 over s. 1 over s squared. So remember, the Laplace of t raised to n, this is just equal to n factorial divided by Sn plus 1. So in this case, our n is 1. So if we take the Laplace, n factorial is 1, then n plus 1, 1 plus 1 is 2. So 1 over s squared. So if we apply that input again in an RC circuit here, let's copy this. Our example, paste. Our input is 1 over s squared. So E of s is equal to 1 over s squared. So this is our E of s. So this will become 1 over s. I over s equals, Is equals this one times this one. So 1 over s squared times 1 over r. Or 1 over s squared times s. So 1 over r. You can cancel out that 1s there. So 1 over s times s plus 1 over rc. 1 over s plus 1 over rc. And 1 over r is a constant. So now, so this is our transfer function. This is our I when our input is 1 over s squared. Then how do we take the inverse Laplace of this one? To take the inverse Laplace of this type of function, this is a proper fraction because the degree of the numerator is less than the degree of the denominator. We cannot divide this anymore. So what we do is we used partial fractions. So we need partial fraction. We need to divide this into two parts. So therefore, I can just disregard 1 over r. I can just look at s plus 1 over rc. This will be equal to a over s. Remember the principles of partial fraction. This is non-repeated roots. Then we have plus b all over s plus 1 over rc. And we need to find for a and b. To do that, we multiply both sides by s plus 1 over rc. So this will be 1 equals a times s plus 1 over rc plus b times s. And to solve for a and b, we let values. There are two methods. The easier method, the first one, we just substitute values for s. S is equal to 0. When s is equal to 0, so our b term here will become 0. So this will be 1 equals a plus times 0 plus 1 over rc. 1 over rc. So therefore, a is this equal to r times c. And next, let s be equal to negative 1 over rc. So if it's negative 1 over rc, this will become 0. So 1 equals, this will become 0 plus b times negative 1 over rc. And b now will be negative rc. And we can now substitute it here. So 1 over this. Now, so we can write that again. This one. This will be the same as 1 over r multiplied by a over s. Our a is rc. So rc all over s. Then we have plus this one b over s plus, because this is negative, b is negative. So this will become minus b, which is rc, all over s plus 1 over r times c. Then from here, we can distribute that 1 over r. So we have c over s minus c all over s plus 1 over rc. We can now take the inverse Laplace. And the i's of t now, the inverse Laplace of I, will be equal to, what's the inverse Laplace of c over s? C is constant. So constant over s. 1 over s is thus equal to t. So this will be c times t. Then minus this one, 1 over s plus 1 over rc. Again, that's just e. So c times e raised to this is plus. So this will be minus t all over rc. And this should be, no, that's t, not plus. And this is our unit impulse response for an RC circuit. Okay, next, so for our unit, this is unit ramp. We also have another one. We call it the unit step. So for a unit step, this is the most commonly used response, unit step response, or simply step response. Unit step response is when the input is just equal to 1. It's not a unit impulse, but a unit step. So if we take r, and we take the Laplace of that, that will be just equal to 1 over s. So if you draw the time domain graph of this one, if it's equal to 1, if this is 1, it's a constant, it's just a straight line. It's a unit step. So the transfer or the s domain equivalent of that unit step response is just 1 over s. So we can substitute that again in our equation here. Let's copy this. this will be our E, A's of S, because that's our input. So we just need to multiply this one with 1 over S. So I's of S now will be equal to this multiplied by 1 over S. It will cancel out S and S. So I have 1 over R, and you multiply it with S will cancel out. So 1 S plus 1 over R C. And you can actually take the inverse Laplace directly from this one now, because this is just E. So I's of T now will be equal to 1 over R times E raised to negative T all over RC. So if you observe this equation here, there's only one term, and it should have two parts, the transient part and the steady state part. But in this case, this is the transient part, because this it has exponential. When t approaches infinity, this will become e raised to negative infinity. If you take that, that's just equal to 0. This means that the current will be equal to 0 when t approaches infinity. So if we analyze that, we have, this is an RC circuit, remember, RC circuit. So if we apply a voltage, which is a step voltage, it's actually a DC voltage. If it's step voltage, because it's just a straight line, it's a DC voltage E. Then if you solve for the current here, when t approaches infinity, that current will become 0. Why? Because the capacitor will be fully charged. When the capacitor will be fully charged, the voltage across here will be just equal to the input voltage. And when that happens, then the current should be equal to 0. Because we know that the capacitor, the current in the capacitor becomes 0 when the voltage is exactly equal to the source. It's just like a battery. When it's fully charged, then there will be no current charging that battery. It stops charging. So it's the other way around for the voltage. For the voltage, you start with 0. Then when time goes by, it will be equal to the voltage. So if we graph that, so if this is our input, that DC voltage E, then what will be the graph of our unit step response? It will look like this one. And if you can see, steady state, when it reaches infinity, this will become 0. This is the transient part, and this is the steady state response. This is the current I's of T. And this value here, this is 1 over R. You start at 1 over R because E is equal to 1. But in general, if you have an input, if the input E can be, or is of S is just equal to E, any constant rather than 1, or is of T, let's change this one. If is of T, the input is just equal to E because it's just a voltage, a DC voltage, then what happens is the current in RC circuit, this is the time response, it will be equal to E all over R times E raised to negative T all over RC. This will be the equation of the current. But if you look at the voltage, if you try to solve for the voltage across the capacitor, it's a different graph. So let's try to do that. So what's the voltage across the capacitor? So we can derive the transfer function for that. So we have, so this is a DC voltage. So E, it's a constant, minus applying KVL. The voltage across the resistor, if this is R and this is C. So the voltage across the resistor is I times R, where we are in time domain. I can just change this one into I's of T. Then This will be I times R, then minus the voltage across the capacitor, VC. And this should be equal to 0. And we need to relate the current with the capacitor voltage. Remember what is VC? This is just equal to 1 over C, the integral of I dt. So if we solve for the current here, we can take the derivative at both sides. So this will be the derivative equals C and I dt. So I, therefore, is just equal to C, the derivative of that voltage with respect to time. So we can substitute it in our equation. So this will become E equals, or E minus I times R, or I is C, dVc all over dt minus Vc equals 0. Then we can now apply the Laplace. So again, E here is a constant, so this will be E over S. It can be any constant, unit or step response, minus the Laplace of a derivative. That's just S times C times V, capital V, in S domain, and minus capital B in S domain equals 0. Then output, solve for the output. So V sub C S plus this one, SC plus 1, SC plus 1. S times C plus 1 is equal to E over S. So therefore, V sub C is equal to E all over S times SC plus 1. Then we can remove that C, or where is our R? I forgot to put R here. This is just I. We need to multiply that still by R. This is also R. And RC. And this should be RC also. So we need to multiply this one with 1 over RC. 1 over RC. So that we have E over RC all over S. And if I multiply that here, this will become S plus 1 over RC. And this is the output now in S domain. And to solve this, we again apply the partial fractions. This is just E over RC, 1 over S times S plus 1 over RC. I actually did this one here, this part here. So we already derived that 1 over S times S plus 1 over RC. And the answer is this one. I can just copy this. Just copy, it's the same thing. And paste it here. And this is the inverse Laplace. Or it's not yet the inverse Laplace, that's just the partial fraction. Then I still need to multiply this with E over RC. This is the equivalent of 1 over S plus times S plus 1 over RC. So if V sub C now, we distribute that, RC and RC will cancel out. This will become E all over S minus E all over S plus 1 over R sub C. Then if we take the inverse Laplace now, we can actually now take the inverse Laplace. So that we have the output in time domain. The inverse Laplace of E over S is just equal to E. The inverse Laplace of this is E times small e raised to negative 1 over RC, negative T over RC. So this will be the step response of an RC circuit with the input of E. And if you look at this, there are two parts. You have E and e raised to negative T over RC. This part here is the transient part, and this is the steady state part. So this will become 0, and this will remain. So if we plot that, so if this is E, our input E, this will be like this one. This part here will be the exponential part, and this will be the steady state part. The steady state, which will be equal to E. This will become 0 when t approaches infinity. And the only value or remains in the voltage is Vc, will be equal to dot E. Okay, so this is the different first order response. We have 3 here. The unit impulse, unit step, and the unit ramp. So for the next topic, we'll be talking about the second order response. But before that, yeah, I want to review this. The term R over C here, there's an R over C, RC. That is actually, we call this one our time constant. This is called the time constant. Time constant. What is the meaning of a time constant? Time constant is this is the time needed to reach 63% of the output. 63.3% of the output. So in this example, if this point here is 63% of E, if E is equal to 1, and this one is 0.633, this part here, then the time, equivalent time, that is our time constant. Time constant. That's the meaning of a time constant. For RL, the time constant for RL is R over L. You can derive that. You can repeat the procedure here. So for the voltage and or the current, then look at, you substitute 63% to the input or the output, then solve for time. Whatever the time is, and that will be the time constant of that response. Okay?